Okay, thank you everyone for coming along to see my talk. What's new in Compiler Explorer? So I'm going to start by some quick fire questions. We've got an awful lot of content to get through, which is a good problem to have in my position. So I'm just going to sort of background in a few moments. So quick fire questions. What is Compiler Explorer? Hopefully most people know what it is. If you've come to a talk called What's New in X, you probably know what X is, so I'm not going to go over that too much. Why is Compiler Explorer? So Compiler Explorer was created as a sort of argument ender. That's what we call it at work. I was having an argument with somebody about whether or not we could turn on C++11 features. Woo, you know, remember that. And whether a range-based for would actually be as performant or otherwise as an index-based loop. We'd had some issues with Java, as it happened, where if you use a range, the equivalent of range for in Java, it creates an iterator behind the scenes, and that creates garbage or whatever. So we've been bitten by that. But I was like, I'm certain it's exactly the same. And we benchmarked it, and it seemed to be exactly the same, but I'm like, no, we can go one further than that. So I wrote a little shell script that was just repeatedly running the compiler and piping the output through some greps and things to get rid of bits. And then I split the screen in tmux, and on one side I had some source code, and on the other side I had the output of the compiler just running every 2 seconds. And I was fiddling backwards and forwards between the implementations, and I was like, look, see, the same code is generated. In fact, better code is generated using a range for than just a regular for loop. So, cool. And then I was looking at the screen going, this is kind of cool. And I went home and I dabbled around with my limited understanding of web programming, and Compiler Explorer was born. So it's an argument ender, but I'm glad to say that people use it for a whole bunch of other things these days. So how, or when? When was Compiler Explorer, or when is Compiler Explorer? That doesn't make sense. It was born on the 22nd of March 2012, or this was the first sort of public commit for it. So it's kind of old now. It's 11 years old. It used to look like this. This is the earliest version in the Git repo. If you check out the first version and just type make, it still actually works mostly, which is a surprise given all the things that have changed in technology since then. And, you know, it has the basic form and shape of the site that you're probably familiar with now. Code on the left-hand side, assembly code on the right-hand side. And you can see that my naming, and you know, we've all seen Kate's talk, naming is hard, we must do better. I mean, interactive compiler is what it was called at the top there, not a very good name. Now, I hosted this at my personal domain that I had for vanity reasons. And so I put it at gcc.godbolt.org because I was running GCC on it. And so it became called GCC Explorer after that. And then once we supported loads of other compilers, it became Compiler Explorer. But of course, most people refer to it by the domain name, which is my name. And it's weird for me to call it that. So I will be calling it Compiler Explorer, even though I know you all don't call it that. So in 2012, we had GCC and Clang. And we just supported C++. The output was pretty unfiltered. It was pretty much the result of what the compiler gave us. It was 5,000 lines of JavaScript, which just shows you how little code it takes to make something like that. It was just me hacking on it. I got some permission from my company to open source it, but it was all me from then. And I was funding it myself out of my own pocket. And thankfully, AWS has a lot of stuff that works in the free tier. And so for the first year, it was pretty cheap. And then it was like 40, 50 bucks a month. And I was kind of okay with that. You know, it's a night down the pub. I could sort of sell that to my family as like, it's a hobby. In fact, my wife says, you know, it's a pastime if it doesn't cost you money. It's a hobby if you have to pay for it. So I was like, that makes sense. Fast forward to 2023, we now have 2,100 compilers or more, which is a lot of compilers. We support more than 50 languages, including like Zig, we were talking about beforehand. We have a number of filters, tools, diffs, loads of stuff that I'm going to go into today. It's 65,000 lines of TypeScript, which, if nobody knows what TypeScript is, it takes all the benefits of compiling, i.e. a very slow and painful process, and marries it with all the wonders of a runtime that is actually completely general behind the scenes, and so it has no real types. So it's the worst of all worlds, but that's how we do web development these days. It's not just me. I have an amazing team. We get loads of PRs from all around the world for people adding their own favorite languages and whatnot. And my sort of core team here is Ruben, Partouf, Jeremy, Mark, Super Greco, and Austin. Phew, I was just panicking that I would forget their real names. Well, one of them I don't remember their real name. Okay, and thankfully, it's no longer self-funded. I have patrons and sponsors which help cover the not insubstantial bill, which at the moment is running. I actually had the alert while I was in Jess's keynote telling me that we've hit our budget for this month, which if you look at the date, you'll realize that we're a bit ahead of ourselves this month, but it's around about two and a half grand a month. But So, it's not insubstantial. It's beyond hobby into small side job. How does it work? Here's a simplified diagram of all of the AWS and things that we use behind the scenes. You're not expected to look at this. It's just more a kind of like, oh my gosh, how do we get here? So again, sort of harking back to Jess's talk from earlier, there's a lot of complexity in here. Unfortunately, I don't have the resources to spend a team to tidy up so much, but we are trying to get there. Anyway, it's all on AWS, lots of EC2 instances and such. And who uses Compiler Explorer? Well, I use it mostly in my day job to, again, end arguments or more to just see how cool the compilers are these days about what kind of optimizations they can do, which code is valid, what code is not valid. And I'm sure a lot of you use it for the same reason in this room here. I'm delighted to see that people who train other people to learn how to use C++, and Peter's nodding in front here, use it, and universities use it for like an introduction to programming, introduction to C++, because what's more annoying than trying to get a room full of 30 students to install a compiler and all the things that are needed to work with it when you can just hand them a URL and say, type in this window. And I know that security researchers use it. We have an API behind the scenes which some third parties use to do work, and I know that security researchers have used it to say, let's try this piece of C code that we know has a vulnerability, and we'll run it through every compiler we can possibly think of on every setting we can possibly think of, and then we can train an AI system to look for the resulting code to tell us where maybe security flaws are, which is super cool. And even better for me personally is that I know that the folks who work on compilers use it both to, yeah, there's a thumbs up at the back there, to be able to have long-lasting links that go to reproducible cases of the compiler, and that benefits me because they fixed issues and I get to reap the benefits. So that's awesome. All right, I'm already 2 minutes over, so I'm going to have to keep going faster, which is unfortunate for you all. Perhaps you'll slow it down on YouTube when you watch it later. So I want to sort of explain all the things that are new in Compiler Explorer, and the way that I want to do that is through some made-up users. So some users and how they might use the site and how you might cover, how I can then sort of show you both some of the existing functionality you probably already know about, but maybe you don't know that there are little options for it, and some of the newer things that are completely perhaps novel to you. And some of these things came in the last week or two, so they're very, very new. So the first user I'm going to talk about is Jordan, and if you'll excuse the AI-generated photographs of these people. So Jordan is a high-frequency trader, much like I was, and Jordan is mostly worried about the performance of his code. That's the main thing. Anything he wants to do, obviously it has to be correct. If you work in high-frequency trading, you can make an awful lot of mistakes very, very, very quickly and lose an awful lot of money very fast, which is a whole other talk, I'm sure. But performance is key and critical to a lot of the stuff that Jordan does. So what would Jordan likely want to do? So maybe Jordan, like me, has a belligerent boss who says, no new things. We can't use new things. We have to write it all ourselves. It always worked this way. It was fine for me when I was growing up, so you can't use the new stuff. So let's start. Now I have to, unfortunately, type behind here, which is where Miro had the problems yesterday for typing. There we are. Lovely. So this is a piece of code that you might write in the old style, shall we say. So we've just got a sum function, and it's been given an array of integers, and it's meant to sum them all up and return the result. Fine. Jordan, though, would like to move to this newer version down the bottom here, where we will use the STL to use the standard accumulate function. Why would not? But for whatever reason, using the STL is sort of verboten in his company. He's like, no, I want to show you that it's good. So how might you do that? Well, you could sort of comment these things in and out. Let me, oops, my key is not working here. There we are. You could comment that in, and then obviously they clash because they've both got the same name, and then I comment it out. And now I can sort of squint at this giant blob of assembly down here and kind of go, well, is it better or not? I don't really know. So the first thing you might want to do is put them side by side. So the way that I'm going to do that is by commenting that back in, taking this whole thing, and I'm going to create a new editor. So we can add a new, whoops, up here, add a new source editor down there. I'm going to paste it in here. And now what we've got is two copies of the code, one old, one new, and only one compiler. So, well, I can add a new compiler for this one. and we can drag it over here. Incidentally, if you've ever clicked on the little add things down here, if you just click them, it'll pop a new one into your window, but you can actually just drag straight from that and dump it wherever you want it to go, which is how I tend to use it. So obviously I need to put the same flags. This is a usability thing. It would be lovely if I could just clone it, but there you go. So I've got two above each other now. Well, I can drag them around. The windowing system lets me drag them things around. But what I can actually do is I can stack these up. So I don't know if you know, you can have little tabs here. So this is like a little IDE. I can have you there, and then I can move you into this tab over here. And now I've got them side by side, but it's still pretty unsatisfying, right? I can see that there's a lot of similar looking magical VP, whatevers. But I can do better than this. One thing we can support is, a difference view. So I can pop out a difference view. Now that's just appeared in the middle. And I can maximize it with the tiny icon, which is almost impossible for you to see, I'm sorry. But you click that, now it's taking up the whole screen. And by default, it stupidly picks the same one twice. But if I pick, for the right-hand side, the new code, now we've got the old compile results versus the new compile results. So it gives me a little bit of an easier way of looking. So immediately you can see that there are actually some more instructions on the right-hand side here. Where there's a grey region over here and a green region over here, we can see that these are new instructions. So that's maybe worth thinking about. I'm surprised that they're not identical, but they're not. That said, it's only a little bit at the beginning. The bit that I would care about is the loop. We know that there's going to be a loop summing up all of these things. And I just happen to know, because I've looked at this a number of times, that this loop is this L4 block here. So from L4, VP add, compare, jump if not equal, go back round. So this is going round and round and round, picking up 32 bytes of values, which is to say 8 integers at a time, and it's summing them up. Did you have an observation there?
Does L4 correlate to like a block in the CFG? Is that what that means?
Yes, L4 is, well, that is a label, and it's being jumped back to, yes. And actually, I'll show you something in a second that will make that even more clear, which is a great segue. So thank you for the question. The question was, what does L4 correspond to some part of the CFG? So anyway, just knowing that this is the inner loop, we can see that on the left-hand side and the right-hand side, they are identical with the exception of a different named register. So on the left-hand side, we've got RDX. On the right-hand side, we've got RCX. That shouldn't make any difference. Even in this circumstances, using a different register name shouldn't make any difference for this kind of piece of code. So I'm pretty confident that those are going to do the same thing in that inner block. And so you could probably use this as pretty good supporting evidence, along with benchmarks and things like that, to show that you could use std accumulate to do the same job that you were using writing out by longhand. But we can actually go one further than that. So I'm actually going to pick up that code there. I'm going to copy it into the clipboard. And I'm going to delete you. And I'm going to actually close a lot of these windows down. And I'm going to paste the assembly. Well, actually, I'm going to change, first of all, the language. So we support lots and lots of languages. I think we've got Zig at the bottom there. There it is. But one of the languages that isn't really a language is analysis. And analysis lets us run some of the machine code analyzers over sections of code. And I'm going to paste in, rather than the default that's here, that code that I stole from the loop body of the function we were looking at. And now I'm going to add a new compiler, which isn't really a compiler, it's the analyzer for this. And I'm going to pick LLVM MCA because it's the one I understand the most. And so what this is using the same tables that LLVM itself uses to schedule instructions and to plan how fast the code is going to go. We're going to use them in reverse to say, like, well, here's some code, can you tell me something about how fast this code will run? And so it's the code that you paste in is assumed to be a loop. And so it's going to effectively paste it after itself over and over and over and over again. In fact, by default, it's going to do 100 iterations of that piece of code. And it tells me that if we were to do 100 iterations of that code, we would see 400 instructions. Well, that checks out. There's 4 instructions over here, 4 times 100. I can do the math. But it says the total number of cycles, machine cycles, is 110. Because internally, the CPU is able to reorder and do even more clever things with architectural magic that I haven't got time to go into here, but is very exciting. So the whole thing will only take 110 cycles. Now, 110 cycles on a sort of average CPU, a third of a nanosecond a cycle. This is like 30 to 40 nanoseconds to do 100 iterations, which is mind-blowingly fast. Even more so when you realize it's actually picking up 32 bytes at a time, which is to say 8 integers. So every iteration is picking up and summing 8 integers. Computers are super fast. Anyway, all of this is more grist for Jordan's mill to go back to his boss and say, look, it's the same, and by the way, this is how fast it is, which is cool. We go analysis. Now, another thing that I find particularly interesting, obviously one of the keys to unlock performance is inlining. I think we know it's sort of the mother of all optimizations. Is the more information a compiler has locally, the better a job it can do about seeing, do you change anything else? No, okay, well then I don't need to worry about recaching some variables I have in registers or whatever. So the thing about inlining though is it tends to cause you to pull all of your implementations up into header files. And that's perfectly valid and it's a reasonable thing to do most of the time. It can become a habit. And so also we're lazy programmers and not necessarily the good lazy that we've been talking about. It is certainly much easier to put the implementation of everything into the header file of a class, even when you don't need to. You're like, it's just in the H file. I'm not going to make a C file to go alongside it. And for me personally, and this is a little bit of a soapbox moment, I don't like that because the more stuff I put, more of my implementation that goes into my headers, the more of my code base has to recompile every time I make a trivial change. So even me fixing a comment that was wrong in the implementation of some internal function can cause my entire code base to rebuild, which is unfortunate, right? I love to have a quick edit, compile, debug, test cycle. Like single-digit seconds is my favorite thing for that. So, and that sort of enforces you to pull things out of the header file and put them into a CPP file. But now I've lost my performance. So how can I have my cake and eat it? And luckily, modern compilers have a solution to this in the form of link time code generation or link time optimization. And Jordan might want to go to his boss and say, hey, we don't have to put everything in the header. We can put it in the CPP file. And I would like to show you how. And he'd like to use Compiler Explorer, of course. But Compiler Explorer historically has only compiled one thing at a time, which means it's very hard to show these multi-translation unit things where I'm going to define a function in one place and use it in another. Luckily, that is no longer the case. And if I can remember how to do this, let me just go to, we good? Yes, looks like we're good. Okay, please hold while we load the site. 300 megabytes of JavaScript. Okay, I'm going to reset the code and UI layout here. And I'm going to start with my square examples. You've all seen this. It's the default one that pops up. I'm actually going to close the compiler. And I'm going to assume that square is going to be defined in one file. And I'm going to add a new editor over here. And I'm going to say int square int. I'm just saying, hey, there exists somewhere else, extern if you want to be really funny about it. There is a square somewhere else. And then int main, I'm just going to say return the square of 42. Now, if we compiled these separately and then linked them, we know that no inlining could happen across them without extra magic flags. But at the moment, we can't even compile these two things. So this is a very new feature. We can add an IDE mode or a tree view. If I drag that over to the left-hand side here, what we can see now is Compiler Explorer is seeing it as a holistic view. All of the panes, which used to be independent and compiled separately and just ran their own way, can now be seen together. And I can add these into kind of the world's simplest build system. So I'm going to call the square one, whoops, if I could type it would help, square, spell, square.cpp, and I've added that to the build. I'm going to call this one main.cpp. All right. I'm also, because of some things behind the scenes that we don't need to go into right now, I can't demonstrate what I'd like to demonstrate without using CMake, because what we want to do is prove that they are definitely compiled independently. So I'm going to add a new file up here, a new source editor. And it's going to have C++ code in it, but it's not going to be C++, but we're going to change that in a second. So we're going to call this project square, add executable square, and I can't believe I typed square several times correctly in a row. Okay, so there's me writing some CMake, and if I add this, don't worry about how complicated this appears to be. I'm showing you the bits, and I'm going to show you how it's easier to do it. CMake list.txt. Okay, so now it knows it's CMake up here, which is fabulous. I'm going to tick the box up here and say the output of this is going to be square. So, okay, nothing's happening. Oh, what's going on? I'm going to stack these up. Well, now I need to add a compiler, but the compiler in this instance needs to be added to the whole IDE in order to see the project. It's a sort of project compiler instead of a compiler for each individual piece of source code. So I add the compiler up here, we drag it over there, and even before I finished dragging it, it had compiled, thankfully. And we can now see I have the output here, and I have the input over here. We've got square.cpp, main.cpp, CMake list.txt, and then the output. And this is a linked output. In fact, if I drag the output window up briefly, you can see it's running CMake, it built square.cpp separately, and it built main.cpp separately. So there's no cheating here. There's nothing up my sleeves. I'm not doing any kind of magic trick on you. But obviously, let's just turn the optimizer on. This is not inlining anything, right? We've got a main function that says move EDI, nor x2a, which is 42, and then it says jump to square. So square was not inlined. But now I can finally do the thing I wanted to do, which is to type FLTO to turn on link time optimization. And we can now see that the main function is just answering with 42 squared. It's just saying 1764 is the answer here. I have pulled the implementation of the square function from another file, and I've been able to combine and link them together and see that the answer is just a constant, which is fabulous, and that's what you want to be able to show when you're inlining stuff. So inlining is possible across units, and it's an important tactic, certainly in my daily life. I have my debug builds without it on and my release builds with it on. Obviously, that was a pain, right? I'm sort of fighting my own UI here to get things done. Luckily, we've made it easier for you. Up here is a templates button. If you click templates, we have a lot of pre-canned layouts of Compiler Explorer. So we've got something which differences to sources, diffs to compilers. Here's a C++ CMake demonstration. So if I click that one, it'll load it all the way up with please load quickly. There we are. And this is a more involved example than even I just showed you, involving multiple files, libraries, and also it has a resource which it is even using. So when we execute the code on Compiler Explorer, all of the source files are available to the executable. So we can actually go up here and I can go in and say, hello, CppNorth. And if you see down the bottom here, we finally actually execute it, and in tiny writing that you can barely see, it says hello, CppNorth. So that's fab. Let me close that. Yes, okay, and there is my cheat. Okay, so we covered a bunch of stuff here talking about Jordan's use case, which is sort of performance-centric. We talked about the basic functionality. I showed you the difference view and the analysis system that we have, and also the number of languages that we have. I showed you IDE mode, which is a bit clunky, but gets the job done. And I showed you that we have templates, so you don't have to remember how to do all of that stuff that I just did. Let's talk about Mason. Mason is a C++ trainer and YouTuber. They have a sort of part-time university gig as well, so they do a whole bunch of teaching of different concepts, both C++ and others, but they like to use Compiler Explorer to show their students both online and also to have their students work on it. So how might you use Compiler Explorer to teach? And I realise that there are people who do this in the front row. So what I might do, and unfortunately font sizes are not helping me out here, I'm trying to make it so you can read in the back here, but hopefully you get the idea of what that's doing there, is I might give my students an assignment to say, hey, can you write me a function which, given a vector of integers, tells me whether or not there is a 0 somewhere in that vector. And I, for example, might come in and write this like the heathen I am, as, for auto x in v, if x is equal to 0, return true. And I realise I've done it all in one line because I'm a horrible person. Else return false. And so that's a perfectly valid solution to this problem. Obviously, we can't see if it's right or not. I've got no test here, which is a terrible thing. We'll come back to that in a second. And there's a whole bunch of gibberish on the right-hand side. And if you're new to C++, that's a horrible distraction, all of that nonsense over there. But first of all, if I was grading this, ignoring whether it was correct or not, I might say, there might be a better way of doing this. Should you not be using like the new ranges stuff? And so I'll be like, all right, okay, let's go and use ranges here. Whoops, if I can actually type. So this might be something like std ranges find v0 is not equal to v.end. And well, the first thing I'm hitting here is that there is no ranges, it's telling me. Let me just make that bigger. There you are, you can see what's going on. Well, that's annoying because I thought compilers supported this kind of stuff these days. Well, obviously, I might have to enable it, whoops, and not by doing that. And I know that there's some arcane sort of command line flag I have to put in that little box up there to say, no, please use ranges. But we have a new feature here, which is this overrides box here. There's just beginnings of a feature which will hopefully help users discover these things more often. So if you click the overrides box, we get a whole bunch of compiler-specific overrides. We can specify environment variables. That's not actually very useful for C++. There are no sane compilers that I'm aware of that care about environment variables, but there are in other languages, so that's why this is here. But we parse the output of -- help and -- help target and all of the things that the compilers can do, and we try and glean some of the command line flags directly from the particular compiler that you've selected. And so in this particular instance, we know how to pull out the target architecture, the tool chain, because it's Clang, and Clang needs GCC to get some of the information it needs, and also the standard version, which is what we need in this particular instance here. So target architecture will have things like all the different random computer CPUs that you might want. Tool chain I already spoke about, but we're interested in the standard version here. So here's my little list of all of the standard versions and their help. So I think I'm going to pick C++ 2B. And for each of these as well, you can make them a little favorite by clicking the star, and then it'll appear up here so you've got quick access to them if there's one that you use over and over again. So now it is going to compile, and it is in fact working. Yay, okay. Now, it's gone green to show you that there is an override present, and obviously you can click and go and look at what it is, but it is slightly hidden from you. If you ever care, incidentally, which flags have been set, this is a sort of like a cheat mode thing here. If you click on this little tick that's in between, it shows you the actual full command line of everything, including all the temporary files and things. There's a question in the front. Yes, Peter?
Yeah, does it also work for MSVC? Because I always have a hard time figuring out the flags that they use.
The question is, does it work for MSVC? Unfortunately, not at the moment, but we can probably make it work with a bit of effort. Where MSVC is a bit of a different case for a lot of reasons, which I'll go into at the end. Actually, while I'm here, and I've been sort of temporarily paused, something I wanted to talk about before but forgot is, I mean, I'm sure all of us have interacted with this gigantic window, and as I've told you, there are 2,100 compilers, and that's kind of a big drop down, right? And so scrolling through that is a nightmare. You don't have to scroll through it. You can type pretty much free-form text in here. So if I just want a trunk compiler that is for x86 and it's Clang, it will find me only the things that match that, and it can be in any order, and it's pretty fuzzy too. You can also tick the little favorite icon here, which will put them all at the top. So if you look at the top of mine, for example, for no apparent reason, I have both Clang and GCC trunk as pinned as favorites, and also the PowerPC 64, which must have been while I was testing something, because I don't ever use that. But even newer feature than that is this little pop-out button here that's also popped up here, and that gives you like a full-on, here's a list of everything in one place, slightly easier to read version of everything, where we can filter by other things more explicitly than just random text that you type into a dialog box. So, you want ARM32 compilers, sure, there they all are. You want just Clang ARM32 compilers, there they are, that kind of thing. And you can favorite them from this view too, but there's a lot of compilers. That's 3 terabytes is our current amount of compilers, which is very many compilers and a whole deployment nightmare in itself. Yes, that's what I would. Oh, yes, and right. So I alluded to this thing on the right-hand side is cool for me because this is what I love is looking at assembly code. But if you're a new student, what you really care about is the output of this, right? But while we're here, you might want to take it as a teaching point and say, well, let's talk about assembly. It's what the computer's actually going to run at the end of the day, so you can't hide for it forever, especially if you're doing systems programming. So one thing you can do is point them at the fact that you can mouse over any of these opcodes and you get some amount of information about it. So MOV, I might be able to guess all by myself what that does, maybe even JNE. But what is this set ni at the bottom down here? This is a weird instruction. So I'm going to click mouse over that, and it tells me, sets the destination operand to a 0 or 1, depending on, okay, right, it's a set if not equal. I get it. We can also right-click and get more information up, and if you really want to bore yourself, you can click on the Intel documentation. It tells you everything about it. And we support x86, we support ARM32, ARM64, and I think RISC-V now, maybe, RISC-V, however you say that. Last of all, is that not everybody learns through reading walls of text in the same way. So, and I perhaps now should have changed the plan with the comment that came from the front, but what we can do is we can add a tool to show the control flow graph. So I'm going to add that and I'm going to maximize it. Normally I'd find some room on my screen, but obviously I don't have here. Let's reset, zoom. So this is a control flow graph that is extracted from the assembly code. We're not actually doing it from the compiler output. We're just reading the assembly code and working it out ourselves. So it's pretty honest to the actual output that's going to the computer. And so in here you can see every basic block, which is a sequence of instructions that has no jump at the end, in the middle of it. And then if the jump is taken, that's at the end of the block, we were meant to follow the green line, else if it falls through, you follow the red line. So in this way, you can kind of see this particular example is there's a bit of setup code and it has a comparison and it goes to the end if the comparison fails. We're not even going to know what it is. I'm not going to go into what the comparison is. Else it falls into this bit where if it fails this comparison, it goes to the end. Otherwise, it falls through. And in this one, if the comparison, is taken, it goes back round to the top. So there we can kind of see the loop body is these two things are going to be repeated over and over again. And there's a couple of get out of jail cards that either stop us at the beginning or halfway through. And then we fall into the same block at the end. So that's another way of visualizing the code. And if you're a more visual learner, that might be a more interesting view to point your students at. But realistically speaking, you're going to want to run the code. I know it's dull and uninteresting to actually get the output of your program rather than the beautiful assembly that's like poetry. I mean, I think it's poetry. It's like Shakespearean poetry, right? You know, not everyone can write it, but we can kind of, and you don't understand all the words of it, but you kind of like follow it, you get the gist of it, right? And that's all you need to do. Anyway, one thing we could do, so here I've actually made a little main function and I'm printing out 1, 2, 3, 4, 5. I'm passing 1, 2, 3, 4, 0 into my function. And, you know, here's the assembly code. There's a lot of it. Once you start calling print routines, it gets very, very awkward. So I'm going to turn this dialog into an executor, which is a dialog, and I'm going to close the original actually while we're here. And now I don't care about running. I know you can tick a box inside that assembly view output to say, and also please execute my program, and then somewhere buried at the bottom of the compiler output is the result of your program. If you don't care about that stuff, then just use an executor view. And the executor view can only execute code. We also get more flexibility. I can add arguments to the program that I can look at here. I can pass in standard in if I want. Yeah, you can hide the compiler output if you care about it. There isn't any in this particular case. So my code appears to work. Oh, and I appear to also have changed it to a std span, which is also quite nice. Anyway, if I were to edit this and get rid of the 1, 2, 3, 4, hopefully it goes vector ... has a 0 false. But, you know, ... is my placeholder for the giant gob of code you have to write to put like a comma-separated list of the actual vector in there. And we can do better. For example, once this makes it into the standard, which it is not quite there in all the compilers, we can use std format or std print. I'm going to use fmt as in the format library. So I'm going to include it up here, fmt format.h. And, could not execute the program. Why is that? Why could you not? Oh, what's this telling me? No such file or directory. Oh, of course, I don't have the format library. You have to go and install it, down. Well, luckily, we got you covered. Up here, we have a libraries little button. This works in all the views. We can click, and we have quite a number, I'm not sure how many, but this many scroll units of third-party libraries that are available. Most are header only, I'll be honest. But yeah, Absel's in there, yeah, for those of you who enjoy such things. So I'm going to look for FMT, and I've got all the different versions of FMT. I'm going to pick 10.0.0. Now it's available to my program. And we can quickly show you the FMT print, and what would this look like? It would be something like vector, and then I have to do like that because we have to escape the stupid things, has a 0 ? Splat, and I'm going to say FMT join I, comma, and then I'm going to say has 0 of I, and if I've typed everything correctly, we should get an answer. I'm just going to say it twice. Please work. Drum roll. No. What? Oh, semicolon, thank you. You see, I've done this so many times, and I got it right. And no semicolon there, though. You see, this is what this is mob programming. I don't know what this is, actually. This is more than that. This is like community programming. Hooray! So 1, 2, 3, 4 has 0, false. And if I put my 0 back in again, drum roll, within a few, thank you for the drum roll in the front there, has a 0 true. Okay, so there we go. So you can use this to actually write simple tests. We have Google test in there as well, so you could actually write genuine, actual, honest-to-God tests. Cool. Another thing that Mason might want to do in their role as a sort of university professor is teach sort of operating system level stuff as well. Like, how does this stuff really work one level down? So see, this is all me, really, of course, so you've already worked that out. I love to show people how the linker works behind the scenes. So here is an example where on the left-hand side, we've got extern int some function. I'm just saying there exists some function. And in the main function, I'm saying I just return whatever that does. And Compiler Explorer currently will be more than happy to do that. It says, yep, I'm just calling some function. And that's because by default, we run the compiler and just say output the text of the assembly that you would feed to the assembler. And we don't do any disassembling. We don't do anything like that. That's our default mode. We used to support, or we still support, link to binary. So if you used to tick it when it just used to say binary mode, this is the same thing here. If I were to click that right now, I get what you'd expect, right? If I try to link this as a program, it doesn't work because nobody has written some function, and I get a link error. But I'd like to see the bit before that. So what we can do now is we can compile to binary object, which means that we link the .o file, and then we disassemble the .o file. But the .o file isn't quite ready to be parsed directly as it is because of what we're going to see now on the right-hand side. So if we look at the opcodes here, 4883 EC08, cool, that means sub RSP, 8, fine. And then we look at the call instruction, and no longer does it say call some function. It says call main +9, which doesn't make any sense at all. But if we look at the opcodes, E8 clearly means, oh, I can't select it because reasons. This E8 up here means a call instruction, and then it's 00000000. It's call to 0, which doesn't make any sense because we wanted to call our function. And if we just carried on, before we implemented this feature, you would have just seen that, and that would have been unsatisfying and unhelpful to everybody. But now we parse the information that's put in a sort of side channel in the .o file that's instructions to the linker. There are some other things I'm going to show you in a second, but the thing that's important right now is that there is an instruction to the linker that says, hey, in byte 5 of this program, please go find some function, the address, wherever you've decided to put it in the binary, subtract 4 from it, and write it in here as an offset. And so what's offset 5? Oh, it's those 4 zeros. So this is the instruction to the linker to come back in and patch this instruction after and make it point to the right location and how to do it. And the linker doesn't need to know what kind of instruction is, how it's used, what addressing mode or whatever. It just needs to know the kind of patch to do. And that's cool. So we can now demonstrate that in Compiler Explorer. And what we can do also is add a tool. So a point of sort of housekeeping here. There are these 2 windows here which confuse everybody, and I'm very sorry. Adding a new pane here, these options are all things that require some level of support from the compiler. Often we have to, like behind the scenes, we have to run the compiler in a new way or a different way in order to support the output from these things. So things like the stack usage thing here has to pass like a flag to the compiler to say, please dump your stack usage to some other file, and then we parse it. Or, you know, if we're running just a preprocessor, or in this instance, we've got a GCC tree viewer, which lets me see the internals of GCC. We know that it's GCC, so it goes on this menu here because we have to interact heavily with the compiler. The tools, though, are things that run in addition to the compiler and are mostly separate from it. I realize it's a distinction that is more important to me than it is to my users, so I apologize for that. And one of the tools that we can run is nm, which if anyone who uses bin utils knows that this is and here's the bug that I discovered this morning, is that this doesn't pick up the default size of font. nm says dump me the symbol table. And so now I can run the symbol table dumper, and I can even pass an argument to say, and demangle it, please. And we can see that here we have an undefined reference to some function. And so this is the information that the linker is using behind the scenes to say, okay, I don't know who provides some function, but this thing needs it. Let me go and try and find it somewhere. And similarly, we can add a tool over here for, what am I doing? readelf. So readelf, every file is an elf file in Linux. Let's do SC to dump everything and demangle. And so this is dumping the symbol table, please. There we go. And so you can see that here it's got a whole bunch of other information again. And again, some functions undefined, main is defined, and then there's all these other weird sections that tell me about where the debug information is, all that kind of stuff. And so again, if you're teaching an operating systems class, or if you're teaching a sort of like compiler behind the scenes class, you can do a lot of it from this view as well. Last of all, I'm sure, or penultimate of all, I don't know if that's a thing, we're all running code checkers, right, all the time now? Yes, lots of nods everywhere, right? It's impossible for a human these days to write correct C++ code. It's impossible with help to write correct code. So let me show you one of the cool things that something like CppNorth, which we support now. CppNorth is a static code analyzer, and I'm padding while it's loading because I don't know quite what's going on here. Please load up. But CppNorth is an open source, free static code analyzer that can look at your code and make some determinations of things that maybe a compiler can't spot because it takes longer, it has to do more deeper analysis, and we don't want to pay for that cost every single time. And because some of these things are more stylistic than they are incorrect. And an example of that is what we have on the screen right now. Let me just make it so you can read the whole thing. So this is my extremely secure, and you should base all of your website security off of it. Validation, is this user the right user? Have they got the right password? We pass the username and a password, and we hash the password, and we check it against the one in the database. I'm not defining these functions up here. They're not important. They return strings, and they take a string by ref value. And I'm sure immediately a whole bunch of you are kind of going, it actually hurts to look at the screen right now because there's something so obviously wrong that it's hurting it. Maybe some of you are not doing that. That's also fine. The compiler is happy with this. I've got all the warnings on. I've got wall, where, wextra. Everything is turned on. This is completely reasonable and completely conformant code. And yet, if I were to put on CppNorth, whoops, which now I can't do because I've made this too small. So I'm going to add a tool, CppNorth. I'm going to put it down here, and I'm going to delete that because we don't care about the compiler's output anymore. Right now, CppNorth is also happy, but I can enable one of the checks. I'm going to do -- checks, checks equals perf star, just to enable all the performance-related checks. And hopefully, CppNorth has said, and then we've got the little wigglies under here to say, warning, this parameter is being copied every time you call this function. You're copying the username and the password. And you don't need to, because the first thing I'm going to do is take a reference to it and pass it on to somebody else who's going to use it by reference. So why the heck don't you just give me a reference? And indeed, it tells me how to fix my code down here, which just because it hurts so much, I'm going to do now and prove that it actually works. So that's useful. And again, that's contentious because, there are situations where it's a 3-byte string, and I'm only putting it in a string to fit an interface, and I don't need to pass it by reference. I can pass it by value. That's fine. The small string optimization gives me everything I care about, or whatever. And that's why it's not a warning in the compiler, it's a warning in the static analysis tools. And just super quickly, and a shout out to one of my sponsors, my commercial sponsors, Sonar have provided us with a license for theirs. And if this loads up very quickly, I'll show you an example. Please work. Everyone has to get off the Wi-Fi as we're using it all up here. So I don't have time to go into the super details of what's going on the left-hand side here, but needless to say, this is concepts and is new code and awesome and fun and cool, but also entirely wrong. But again, the compiler is happy with this. Everything about this is super fine. I am going to add Sonar as a viewer, and it's immediately going to underline these and say, look, these things don't do the thing that you probably think they're doing. All you're doing is checking to say, does this compile? Are these compilable? You're not actually checking, is it an integral or is it the same? And again, I don't have time, unfortunately, so I can talk about this with you afterwards if you want to go into that in detail. So what do we cover in this? Quite a lot. I showed you the tooltips and the control flow graph. There are a mass of binary tools that run on your code after you've compiled it. The overrides window gives you a principled way of adding new command line flags, especially the more esoteric ones that have thousands of different options that you can never remember yourself. I know I can never remember what architectures are supported in which things. I showed you the static analyzers, I showed you the execute-only view and the libraries. Let's talk about Joanna. Joanna is one of those people that compiler authors love to hate. She writes the kind of code that makes the compiler fall apart because it is at the absolute boundary of what the language kind of specifies. She loves to dig deep into the compiler spec itself as well and likes to understand how the optimizations inside compilers are done. And yeah, she generally writes torture code that's awesome. So I don't have a small enough example of the kind of Joanna code I'm talking about to show this. So I've boiled it down to the world's simplest and surprisingest piece of C++ code, which again, I should have clicked on earlier to give it some time to load up. Talk amongst yourselves. So who all knows what C++'s most vexing parse is? Yeah, there's 2, 3, 4. Okay, there's half-hearted hands kind of going, I think I do. It's just terrible. Okay, so this is a piece of code that takes a floating point number and in a terrible way that you should never do, casts it to an integer and tries to return it. Or at least that's the intention of this code. But on this second line here, where what it looks like we're doing is constructing an integer from a floating point number and then storing it in an as-int variable in the initializer. We're not. What we're doing is defining a function. But it's super unintuitive that that's happening. Luckily, the compilers actually are really good these days. So Clang says parentheses were disambiguated as a function declaration, and it says how to turn it off and everything. And that's cool and all, but I know how to fix it. It tells me in the warning message. But what is going on here? What we can do is add a new view. Now, because I've got a Clang-based compiler in this list, some of the options in this drop-down have popped up to show me Clang-specific things, including device views and AST views and IR views. And I'm going to look at the AST. So Clang lets me dump the abstract syntax tree. Try saying that 2 times. And here we can see, and like even with all the highlighting, as I'm mousing over it, showing you the various different parts that are valid, I can see what Clang thought my code was. So it parsed it as a function declaration, which had a parameter thing and had some statement, which was parsed as a declaration statement. And specifically, it was a function declaration. And so now I can kind of see where that is going on. And because, again, it hurts me so badly, I can fix it in this way, if I could type. And just because that's a C-style cast, well, not even a C, it's a constructor-style cast, I will also fix that here just because it hurts me to see it that way too. So it's all silly code, of course. Don't write code like this, please. But, this now compiles. I can now see the parse tree. I can see that it is now a variable declaration and all of this stuff here. And so if you are pushing the boundaries of what is valid C++ code, this might be a useful view for you to understand why it is. There's a question in front. Go, Peter.
The example would have been more interesting if you had used auto at return time.
Okay. The observation was the type deduction might have been more interesting. Okay, I don't have time for that, unfortunately, because I'm behind, but yes. It's worth also noting that we have links up here to CPP Insights and QuickBench, and clicking the CPP Insights one might give you an even more window into that kind of thing here. We take your code and put it onto a sister site, or a sibling site, I don't know anyway, okay, moving on quickly, because I'm looking at my time and going, oh dear, I'm going to give you a hard time, I'm afraid. One of the things that one of Joanna's favourite pieces of code, my favourite piece of code, sorry, is the kind of awesome things that compilers can do. Compilers are amazing. So on the left-hand side, I have some pretty straightforward imperative code that you can't quite read, but now you can, that says, I would like to count the number of 1-bits in this number. Okay, I have a 64-bit unsigned value, and I would like to know how many 1-bits there are. Don't ask me why this is useful. It honestly is. And so I start out by saying, okay, well, let's keep track of how many I've found so far, put it to 0. And then I say, right, while the value has any value at all, like while it's not equal to 0, there must be at least one 1-bit in here somewhere. So I'm going to increment my count by 1. And then this funny Byzantine game programmer hacker trick here that I learned from a book, and I encourage you actually to sit down and work out why this works. It's fun. You write out a binary number and see why it works. It's cool. But this clears the lowest currently set bit. And so now I go round my loop again, and if that now was the last one, we're done. Otherwise, I know there's another 1-bit in here somewhere, and I just keep going round, and I count them up, and that's fabulous. But the coolness of this routine is totally offset by the fact that the compiler looks at that and goes, I got an instruction that does that whole routine. And like, whoa! And if we look on the right-hand side here, pop count. This instruction calculates the numbers of bits set to 1 in the second operand. That is a marvel of engineering. It has completely read my loop, and I could have written this a number of different ways that all amount to the same thing, and it kind of goes, I got you, I know what you're trying to do here, and I've got an instruction that does that whole thing. Is there a question in the front, or is that a stunned?
Well, this is like not related to Compiler Explorer, but like, is there a way, if you know that there is a machine instruction that like, or an assembly instruction that does exactly what you want to do, like, is there a way to just put that in your C++?
So the question was, is there a way of telling the compiler this is what you would like it to do directly rather than relying on it? There is, yes. You can actually use standard bit set, and you can say count number of set bits in that for one way. But there are also intrinsics that you can call, and but they rely on certain things being set in the compiler, and they're not necessarily part of it.
Function. Like, that is like a very useful
yes.
assembly instruction.
You can You can call it, but through sort of vendor-specific extensions called intrinsics that amount to that, and they're different for different platforms. And obviously, this is super specific to an x86. Now, obviously, ARM chips have their equivalent and all that stuff. So there is I think GCC calls it __pop count or something like that. It's population count, like it says here. So anyway, it's cool, but here's the cool thing. You didn't have to know that there was an instruction that did this. The compiler did it for you. So there's a certain benefit from that. So that is pretty awesome. Oh, sorry, hang on. Whoops. I forgot to do the thing that I meant to do now. We got derailed, which is not going to help my timing anything. Okay, please hold. Caching should have worked here. So that's awesome and all, but I'd love to know how Clang is doing this. Right? I know somewhere buried deep in Clang, there's a bit of code that goes, I know what's going on here. Now, I can't tell you exactly where that is, but I can certainly help you find where to look. So one of the views we've got down here is the optimization pipeline for LLVM. So we can pass flags to the compiler and say, can you just tell us everything about what on earth you're doing? And I'm going to maximize this because we don't need to look at anything else. And this is our presentation of that view. On the left-hand side, we see all of the compilation passes that have gone through, and Clang has many of them, and by many I mean, this many. So the way that it works internally in something like Clang is that your code is parsed into a very simplified intermediate representation. It's quite low level. LLVM, in fact, is the low-level virtual machine that this is so speaks of. And what we're showing here is the before and after code for each of the passes. So on the left-hand side, this is what the input was created by parsing the input, and then having applied the annotation to metadata pass, it's the same on the right-hand side. It's a diff view. They'd be colors if they weren't. And every time it's different, we highlight the pass in green. So this green pass down here is the first one that actually made a change to the intermediate representation. It's the SROA pass, which I just happen to know is the scalar representation of, scalar replacement of aggregates. And if I click on that, now we get a diff. And all this stuff on the left-hand side, which was like making all of these local variables on the stack, has been removed and turned into just named things on the right-hand side, which I don't have time to go into detail here. But anyway, you can see how you could kind of click around here and sort of understand and get the gist of the kind of things that are changing every time these passes trip and say, oh, I can improve this. And I also happen to know that really there's a lot of stuff that goes on which is normalizing the code. That just means it doesn't matter if I wrote a while loop or a for loop or a do while loop, it all gets turned into a canonical form, which makes it really, really useful later on because now I can write a matcher inside the Clang code base that says, if you see this sequence of things, it's doing this other thing. And they'll always appear the same. And just to get ourselves some satisfaction, I'm trying to find where the heck it is. No, I've missed it. Darn it. Simplify, combine, loop deletion pass. I happen to know that the loop deletion pass is the thing that does this in this particular instance. So here we can see on the left-hand side, we have a while body all around here, and there's the obvious bit in the middle where it's doing all the anding and subtracting and comparing and whatever. And on the right-hand side, after it's done the loop deletion, the sort of vestigial form of the while loop is still there with the beginning and the end in the middle, but the whole thing has been pulled up to this cool i64 CttPop.i64, which is LLVM's internal way of saying there's a magic machine instruction which does this. And then later on, it all gets cleaned up. And as we get further down this list, so now I could actually like Google inside or search inside git grep inside the code and look for loop deletion pass, and I might have a chance of finding this amazing thing, and then go and find the author of the code and shake them by the hand and say how clever they are. And then right by the very end of this, the code looks less like LLVM and more like actual machine code. And then obviously the machine code is generated from this. Here there's a pop count and a conditional move, which the existence of the conditional move is an entirely hour-long talk in itself. So we're not going to go into that right now, as I have very few times left. Last of all, if you're Joanna, you're always torturing compilers, as I've said. And one of the things you might do is use some stuff which isn't supported on all compilers. I'm going to turbo through this in order to get to the next bit. I can add a conformance view, and a conformance view is essentially as many compilers as you can wedge in the screen, and I can say, I want this one to be x86 trunk, I want this one to be power PC Clang, and I want this one to be x86 for Clang, whatever, and then I can put the flags in here, which would be std equals C++ to A. I realize I'm having to do this here because we don't have a way of getting to the overrides from this view. Oh, that's not right. Okay, so apparently PowerPC 64 Clang is not up to date with the standard. I mean, boohoo. We can do MS trunk, MS VC latest. There we are. Okay, ARM 64, sure. And here, unfortunately, this is stood C++ laces, which is exactly what Peter was asking at the beginning there. So now I've got like my 4 compilers and I can start typing my code and editing it over here. And anytime it doesn't work, we get a little red icon here and I can click all these buttons over here to open it up in a new view and actually debug it. But what it means is that you can like have, you can create a short link to this with just your N compilers that you have to care about. And then you can tinker away to your heart's content and see, yes, it still compiles on all the compilers with all my flags. Shorter than I wanted. But we covered the AST viewer, the LLVM pass viewer. There's an equivalent for the GCC one. It's just not as developed as the LLVM one, and the conformance view there as a way. So let's talk about Matt. Matt is a late 40s software developer who is trying to recapture his youth by emulating the computer systems that he grew up with. Matt also runs a popular C++ website, and he's seeking ways of getting all these things together in one place. So what Matt has done is, oh, please load. Come on, do it. What Matt has done is taken some of his hobbies and put them all in one place. Now, I wish I actually had, Matt had actually written this code here, but actually Matt's best friend from school, like literally 11 years old, no, I've known him since, wrote this demo for the BBC Micro, which you might remember as a 1980s British computer, which I don't think necessarily made it over here, but nevertheless, you've all seen like an Apple II or something. It's kind of the equivalent. And yeah, here's some code on the left-hand side, which is, assembly code still, so it's not really compiling it, but it needs to be assembled, and there's tables that get generated and stuff. And here is what it comes out the other end. It's a whole bunch of, also assembly code, it turns out, because if you assemble assembly code, you get assembly code or machine code, right? But now I have to reload, unfortunately, which is going to take 14 years. Obviously, you'd like to see if it works or not. And down at the bottom here, a little pop-up has said, click here to emulate. And so we can, in fact, boot up a BBC Micro from 1984, and we can run a version of it here. And yeah, that's bringing together, as I say, all my favorite things. Okay, I have 5 minutes, but wait, there's more. Clicker work, damn it. There we are. We have statistics, so we log a whole bunch of stuff. It's an open source project. Everything about it is open source to the best of my abilities because it makes my life easier if other people can help me. We have all of our infrastructure, all of our AWS nonsense, except for obviously the private keys and things like that, are all open source as well. So, if you want to add a compiler and all that kind of stuff, you can send me 3 PRs and it's on the site within a few days. We export our statistics, so you can see that at stats.compilerexplorer.com. Having seen Jess's talk from earlier, I'm really, really interested in what I can do in the space of other metrics that we can do internally to make the site faster and cooler. We support GPU execution now. So Amazon have instances that have GPUs on them. If you want to try your hand at CUDA, if you want to try your hand at whatever the other one's called, can't remember. Anyway, you can run the code and actually execute it on a machine that has a GPU, which is not cheap, unfortunately. And so sometimes it's not always there. We use the tier of Amazon where we have to bid for the machines, and there's a sort of threshold price, and sometimes we don't get them. We are actually running our own Windows machines now, and that allows us to do Windows compilation on our own hardware. Our own. Because we are in control of the security there and we're pretty confident in our security, I got a feeling this is a thing, we can support execution of user code on those Windows instances. We're in negotiation with Microsoft about getting the support we need from them to be able to run the MSVC compilers. Total sidetrack, Microsoft actually host and run the MSVC instances on a separate site. We proxy out to them, and it's very, very helpful, but it means that they're obviously understandably a bit funny about running in their corporate network other people's code. It makes sense. What have I got? What dreams have I got? Obviously, I'll continue to support more compilers, languages, platforms. We pretty much have an open door policy. If you send me a PR, I'll merge it. We'll have your language in there. We've got a number of smaller languages that maybe even only the author is used. I'm looking at the back of the room there for somebody who I know is doing exactly that. I've got a love-hate relationship with supporting logging in. On the other hand, I have a very, very clear and straightforward privacy policy. It's about the only privacy policy ever, I think, that has got fan mail about how clear and easy it is to understand what we do with your information, which is to say, as little as possible, we don't want to know what you're doing with the site. There's Yeah, but logins kind of break that, because if you want to be able to like save short links and have them associated with you, and I know who you are, now I've got to worry about GDPR a lot more than I do already, and all those kinds of things. And I'm just a dude, and I don't have time for this. So logins, I'd love to support, and we might do, and we may even be able to do things like increasing the throttle rate for people who are logged in, because we can always, send them an email and say, can you please stop hammering the site, rather than just having an arbitrary high level. People have asked for live updating links over and over again. That is a link where I can share a link with you, and then as I'm changing it, you see my changes, and that would be super cool. It's a lot of work, and I think we can do it in a limited way. It would be harder if it was bidirectional, if both people could hack on the code. It would be cooler, but it would be a lot harder for us, right? We're pretty much dumb. And then in the sort of full culmination of all of my hobbies, an x86 simulator would be in there. So you saw the MCA, the machine code analyzer, and it kind of has a simulator to be able to determine how fast things are. My other passion is like reverse engineering all this stuff. And so I would love to come up with not only can you compile your code, not only can you look at the assembly of the code, not only can you single step through the code in sort of an emulator for each x86 instruction, you can also see the L1, L2, L3 cache, the branch predictor, all of that stuff. I'm getting chills just thinking about it. It's so cool. Maybe when I retire, which, might be a while off yet. Anyway, please work. Last slide. So I'm going to hit the time budget, and I'll hang around for questions at the end. I obviously have to say thank you to my sponsors. They make the site possible. I can't afford it to run by myself. So my commercial sponsors, my patrons, and those who support me on GitHub, and the team and my company who let me come out and talk about this kind of stuff. So thank you, everyone. Thank you very much indeed.